a couple of items to. So I spoke to the TQIP coordinator here within IIT Bombay, and they said they will be uploading it on YouTube. However, what I plan to do is I have all your emails. I will just put it in my Google Drive and share some of the videos and the lectures. And the lecture materials I've collected, I just wanted to add few more lines there, here and there. Those things I have added as well now, and that part I will upload those PDFs through Moodle tonight. Regarding the videos, I will share them through the Google Drive information. I'll send them individually to your email addresses. Then the last 2 days, last Saturday and Sunday, the first day was mostly focused around the introduction, spending some time on what are the terminologies and some of the basics of packaging, and then how thermal design was studied, and then we focused on conduction part of the electronics cooling. Then I moved to natural convection very briefly in the second day. Today I'll go to forced convection, and this is just a placeholder slide, and I'm sure many of you know very well about the forced convection, full flow or a flat plate case, and you always have boundary layers develop over the given solid surface. So we'll skip this and get to the meat of the stuff. And so that's just a placeholder slide. And in general, as you all very well know, that there's a typically one deals with what would be the range of heat transfer coefficient, average or mean heat transfer coefficient, and for flow or a given surface, or forced convection in air and water and liquid metal and so on. Liquid metal is actually coming back to electronics cooling as a possible medium for cooling itself. There is a metal low temperature eutectic alloy called gallinston that is liquid in the room temperature range, and that now people are exploring as a possible means of cooling electronics. However, it is very corrosive, so the metal needs to the compatibility of the heatsink material needs to be carefully chosen with this liquid metal. Nonetheless, it is being studied these days as a possible medium to remove heat from these electronics chips. Then we have boiling heat transfer coefficients that are quite close to 10,000s or tens of thousands, and then condensation. So you see these boiling and condensation in the heat pipes and others that I'll be discussing briefly later. In general, one of the biggest challenges in dealing with cooling of these motherboards and printed circuit boards is that there is no geometric similarity in electronics cooling. That is, each board will have different components in them, and you will end up having to manage so many different length scales and geometric scales that offers no similarity to that one can derive and do some experiments and approaches. And there is substantially the entrance effects, exit effects become also important because of the change in area. So these days, most of the companies employ packages like IcePAK and to study or develop cooling solutions for these motherboards. Analytical solution is really not useful from the context of designing these boards. However, they are used as a way of designing heat sinks, at least as a starting point design, initial guess for optimization of a heat sink. So the substrate conduction plays, so you have the conjugate heat transfer happening in these, and the heat transfer I will discuss a little bit more, is actually much more involved than what we typically teach in a class, where we talk about flow through a pipe and a flow over a flat plate and tubes and so on. Here there are innumerable number of heat sources that makes it really hard to choose a heat transfer coefficient and what. So we'll discuss some aspects later in the. As you all know, if you look at heat transfer modes, there are primarily two heat transfer modes. One is conduction and radiation, while convection is sub part of conduction. However, often in textbooks, we see that conduction, convection, and radiation are the heat transfer modes that are discussed. Now, all these three heat transfer modes are in place in a given force convective flow over a printed circuit board. I will discuss heat sinks in the probably either today itself or start today itself or probably tomorrow. However, one of the biggest challenges is system level. If you look at a system that I've shown here, so here's a Xeon Phi Knight's Corner card, and you can see that all these VCRs are voltage regulators. GDDR is the memory device. The KNC is Knight's Corner package, Xeon Phi package here, and all these dissipate heat. So at a system level, even though this is a very much a subsystem, but if you were to look at a server board or a desktop board, the system level will involve about 100 centimeter or so, roughly speaking. So the Reynolds number, if one were to calculate based on the velocity and the system size, then the Reynolds will be in the 100,000 range. If I go to the PCB level, that is this motherboard level, then it will be on the order of 10,000s. And at the chip level, if I'm just focused around how to cool this chip, then it will be on the order of thousands. So you have, depending on what length scale you use, you get different Reynolds number. How do I decide which Reynolds number is the best? Or how do I decide what modeling or what technique to be used, turbulent model or laminar model? Now, it all varies. So, but in many situations, when you're talking about from a motherboard perspective, flow or a printed circuit board, you always see that it is highly turbulent because of the height variation in the system itself. So we have always talked about it. So there are many situations that arises. If you look at this as a cross-sectional view of a printed circuit board, there is a heat source here or a chip here. There's another heat source that is height of B2, then B3. So B1 is not equal to B2, B2 is not equal to B3, and L1 is not equal to L2, and L2 is not equal to L3, and the spacing between them are not same either. In such situations, now you have, and also this is not covering all the way to the top, so there is a lot of flow bypass. So here's an example. This is a cross section of a heatsink, parallel plate heatsink. So depending on how this heatsink is placed, if my duct is enveloping the entire heatsink, then we say heatsink without a tip clearance. But if I have a space on the top, it is heatsink with tip clearance. And heatsink, if there are flow paths around it, then it is heatsink with tip clearance and bypass. So this is a very common situation in telecom cabinets and even in server boards. And this ducted heatsink configuration is almost impossible to achieve in many occasions because of manufacturing tolerances. There will at least be some tip clearance on top of a heatsink. So what really happens is, if I'm bringing in a flow that, because of least resistive path, most flow would want to bypass the heatsink to go through the in between the fins. Instead, it would want to go above it. So how to quantify it? And the situation becomes even more harder when you have side bypass as well. So designing heat sinks when you have bypass becomes extremely challenging. And so depending on the surface roughness, incoming turbulent intensity, and so on, now you see extremely complex flow behavior in many of these electronic systems. and and so that really leads us to one simple statement, that generalized statements are difficult. Generalized relationship for any given board is not feasible. So one has to really look into each and every time. One has to look into uh, the given board and its given characteristic geometry, and then simulate for each and every board individually. Anytime you make a change of component in the board itself, then you have to redo your analysis. That is the real time spent by many of the engineers in all these electronics cooling industry, where thermal solutions are sought after. So because you have both size and shape of the geometry that is changing. As I discussed to you previously, Reynolds number requires, if I were to use Reynolds number as a way of using for similarity, geometric similarity, and exploiting Reynolds number, it has to require the scaling, geometric scaling, to be same. I have a tube, and I have a 6 millimeter tube, and then I calculate a Reynolds number and calculate its friction factor and nozzle number. And if I move that from 6 millimeter tube to 10 millimeter tube, as long as it's a tube, then I can use the relationship that I had developed for 6 millimeter tube, because I have non-dimensionalized it. So I can use it for 10 millimeter cube. However, if my tube becomes some other shape, instead of being circular, if I make it square, then I can't exploit my relationship that I had developed for circular to square. So that is the situation, that for each and every single system, the geometry is changing. So there is no single relationship that one can develop. And even though there have been some attempts by some of the work, some researchers, to at least capture some global scale effects, however, they are not quite um, robust. They have the weaknesses. So in direct flow over PCBs, the typical velocities that are observed for natural convective flows over a printed circuit board or motherboard is about this much, 0.1 to 0.25 meter per second. Force convection is about 1.5 to 2.5, and mainframe or desktop computers is on the order of 5 to 8 meter per second. These are rough order of magnitudes. It is not to be treated as some sort of accurate numbers. Whenever we talk about force convection cooling, then one has to deal with fans. So in a fan, you typically look at a fan curve that looks like it, like this, which is pressure drop is the vertical axis often. And here, many of the meetings or many of the companies often specify in inches of water, which is, if I want to convert that to pascals, then it is rho GH. Rho is density of water, G is the acceleration due to gravity, and H is the height of the water. Is what is specified here, inch of water. And Q is the volumetric flow rate, that is meter cube per second. Here CFM is used again because of industry norm. CFM is cubic feet per minute. However, of course, you can convert these into SI units and operate. So the fan for a given RPM, revolutions per minute, will have a behavior as shown here by this curve. That is called a fan curve. Points curve 1, 2, or 3, or 3 curves depending on if I have a fan and I put a heatsink there, then the heatsink offers a pressure drop for a given flow rate. So depending if I keep increasing the flow rate, the pressure drop keeps increasing. The point where the system pressure drop meets the fan curve, this is often called the operating point. If I change the heatsink from heatsink number 1 to heatsink number 2, then I get this second curve, B, the operating point B. And if I change it to another low pressure drop heatsink, then I get curve number 3. So what really happens is that in a fan curve, you always see a knee, and then there is a slight rise, and then it falls off. This knee is a problem region because now I can have, as you can see, for a given pressure drop, there are 3 possible flow rates that a fan can generate because it is very unstable. It can give me a flow rate Q1 or give me a flow rate Q2 or even give me a flow rate Q3. So it is always better to avoid this knee. And so this is also a problem in terms of operational perspective, is that if for some reason the heat sink is plugged, this flow, or if there something happens, then this flow will start to come to this unstable region. So it is always better to come to this region. Often most of the heat sinks or systems are designed in such a way that it is away from the unstable region and always towards the higher flow region. So if this is my operating point, then I get to see that this is where the slew system. But you have to realize that this is for a given RPM, that is revolutions per minute of the fan. If I change that RPM, if I increase it, it will shift up. If I decrease it, it will shift down. It won't change the shape of the curve, but it will be similar. The curves will be similar, except that it will either be shifted up or down depending on the revolutions per minute as per fan laws. So generally, friction factors are the ones that are used for flow between printed circuit boards and so on. However, these frictional losses or whatever that one calculates using these relationships, they are not, as I said, realistic for any given system. They just give some rough order of magnitude rather than being accurate, because as I mentioned to you, the geometric scales change from a given motherboard to another motherboard. So with that kind of setup, just getting these type of relationships, there have been attempts to give some sort of a correlation for pressure drop. However, those pressure drops are not useful at all. They just give only some guidelines of what could be happening. So again, the same issue arises with heat transfer. With the heat transfer, it is actually quite even more involved. That what is my heat transfer coefficient? How do I choose my heat transfer coefficient? I'll explain this. There have been some correlations and so on. I'll keep these in just for the sake of completion. However, these correlations are not useful when it comes to real boards. They just give rough order of magnitude because they assume some equidistant spacing of these heat sources and this and that, which is never the case in a real board. So what happens if I have this is a simple thing that we typically deal in the class. If I have a heat source and there is a plane, there is a flow between 2 parallel planes, and heat flux is applied on top and the bottom, then my average heat transfer coefficient is given by this relationship. 140 divided by 26 minus 9 into Q2 double prime divided by Q1 double prime. And if my Q2 and Q1 are equal, that is if it is a symmetric heating case, then I get an average Nusselt number of 8.2. And my non-dimensional temperature looks like this. And the bulk temperature is given by this dashed line. if I make my top side adiabatic, then my nozzle number drops right away from being 8.235 to 5.385 because my top wall is adiabatic. Now this temperature profile of the fluid meets at a perpendicular angle with the top wall. That's the bottom is the heating wall. You can see that already based on the situation, now my nozzle number has changed. Well, it's just such a simple case. So what happens if I have a heat source that is only not my entire length is a heat source, but I'm is not a heat source, but I have a heat source only for a shorter length of L. There is some sort of an unheated starting length, and then there is heating happening. So your velocity may have reached a fully developed flow regime before it enters the heat source. However, the thermal boundary layer just starts here. So what length scale should I use? Should I use the height of this channel as my length scale for calculating Reynolds number? Should I use the length? Because the question is whether should I treat this problem as internal flow or external flow. That comes into picture. If it is an external flow, then I can say that my length of my heat source can become the length scale appropriate to calculate a Reynolds number. If it is an internal flow, I'll use the hydraulic diameter of the duct to figure out my Reynolds number. In fact, in some situations, because of the conjugate nature of the problem here, that is, some conduction is happening from this heat source to this board, and then it can dissipate to the top. Then the D also come into the thickness of that heat source also come into the picture. So you have now multiple, this is a very simple 2D situation. You have now multiple length scales that one has to deal with. And what heat transfer coefficient will I get? Because if I use height, then my Reynolds number will be slightly higher, so I will predict a higher heat transfer coefficient. If I use length, the flat plate based correlations will always fetch me lower heat transfer coefficients. If I use D, I'll get even lower because the thickness of the heat source is small. So the question is, how do I pick a length scale? And we can talk about this a little bit again in a different perspective. Here's a uniform heat source. Should I use flow over a flat plate for this case, or flow between if my height of the top wall, which is, let's assume that is adiabatic, the heat source is on the bottom wall. If that height is tall enough, then can I use external flow assumption? The question is the flow, what length scale? Then if I shorten that length scale, if I have multiple heat sources, then what is my length scale is the question that typically arises. So one of the things is that if my height, one of the simplest option to explore is this example that I just discussed here, is that if my boundary layer is not, if my velocity boundary layer is not even interacting with the top plate, if the top plate is far enough for the cases that I'm dealing with, then only under such very corner or limiting cases one can use external flow type situation. If my velocity boundary layer is interacting with the top plate or the boundary layer that develops from the top plate, then one has to deal with it as internal flow. So in this case, one has to use an asymmetry boundary condition because the top plate is not dumping heat, and this is the situation where we obtain this relationship. There is heat flux coming in from the bottom wall and no heat flux coming from the top wall. So the average nozzle number is 5.3. This is not the half of this. Half of this will be 4.1. However, it is 5.3. So So one just has to really look into it. Now, if I have a heat source that starts only after certain length, then the situation again, should I use flat plate or correlation, or can I live with internal flow correlation, is a question. In some of the cases where you deal with conjugate heat transfer, the thickness of the heat source becomes actually a viable length scale as well. And some of the conjugate heat transfer problems say that Reynolds number should be defined based on this thickness of the heat source. What happens if I have multiple heat sources? So all these cases now give us an opportunity to really improve the concept of heat transfer coefficient to something that becomes, we want to find a heat transfer coefficient, because the way the Nusselt number was obtained was that it should be invariable. If I use the Nusselt, if I say Nusselt number for flow through a pipe which has a constant heat flux, then I would say it's 4.364. And whether the pipe diameter is 6 mm or 10 mm or 100 mm, I should get the same Nusselt number. So can I get an invariant descriptor of heat transfer coefficient in such a complex system is the question. So as you all know, there are multiple options by which we can define the heat transfer coefficient. So one is the surface temperature, that is clear. So we say heat transfer coefficient as flux divided by delta T. That is our typical definition of heat transfer coefficient. Heat flux dissipated by this heat source divided by the surface average temperature of the surface minus some reference temperature. Our question is, what should be the reference temperature? Should it be the inlet temperature? Should it be the mixed mean, which is the bulk temperature? When you do when you take a slice and do a bulk mixing, essentially enthalpic mixing there. Then the third definition is LMTD, which is often referred as the log mean temperature difference. Should I use the log mean temperature difference as my reference temperature? And the last one is the so-called adiabatic heat transfer coefficient based on adiabatic temperature. We'll discuss what is adiabatic temperature for in this context. Let's first look at the definition with inlet temperature as a reference temperature. Here I have P1 is the power dissipated by this first heat source, and it has a wall temperature. Let's assume the heat source power is uniform, not the non-uniform case that we discussed last week. Let's assume that it is uniform and it is and its wall temperature is 1. So then my inlet based heat transfer coefficient can be defined as Pi, I being 1, 2, divided by Tw, I minus T inlet. So this has some issues clearly, because when the flow goes over this heat source and I am dumping some amount of heat into the airstream, then the airstream gets heated. That heated airstream now meets the second heat source. So now you run into a situation that if I base only on this inlet temperature, then definitely my heat transfer coefficient, even though they may P1 and P2 may be of equal power, now I'll find that when I calculate a heat transfer coefficient, this is going to be very different from this, because here the wall temperature T wall 1, let's assume that there is no heat conduction happening through the green board, the PCB that I'm talking about. There is it's insulated. Only all the heat is dumped into the airstream, just for simple discussion. So if the heat flows into the airstream will pick up some amount of heat. So my airstream temperature will rise, and this heat source, on the other hand, will also have the same power. Let's assume that P1 and P2 are same power. Now for the same power, now I have an inlet temperature that is slightly higher than this inlet temperature to this heat source. Now this wall temperature will go up. By what amount we won't be able to predict. However, we can be assured that you can look into you can do the calculations as well, that this inlet based heat transfer coefficient definition will not work, because every heat source, as you go add more and more heat sources, the heat transfer coefficient will appear as if this heat transfer coefficient is higher than this heat transfer coefficient. So because the delta T will keep dropping a little bit. So then what about mean temperature based heat transfer coefficient? What really happens is, if my heat source is not very far off, if my flow comes in and I pick up some amount of heat and I'm dumping that heat into the stream, if the next heat source is very adjacent to each other, this volume or space, empty space, is not sufficient to mix the flow thoroughly. So the mean temperature of this airflow, actually you can calculate it. However, the mean temperature of this airflow is not going to, if you calculate a mean temperature, it will be lower. However, the temperature air profile, air side temperature profile, I'll show here. I show here that situation, that if I have a mean temperature, so inlet is, this is the lowest point, comes in, as heat is dumped from this heat source, it goes up, and then there is no heat source, so it stays flat. So that's what the mean temperature looks like. However, if I look at the actual airflow temperature, air side temperature, it will look like this. It will be a lot smaller at the lot lower at the top, and it will be much hotter very close to the heat source. So even the actual profile will have a temperature profile looks like this, because the y is the vertical axis, this axis, and the horizontal axis is the temperature. So I'll see hotter temperatures closer to the heat source and colder temperature at the top, because the flow, if the spacing between the heat sources is small, then the flow will not have sufficient time to mix. So if you don't have sufficient time to mix, then this same profile will hit the next heat source. That means even though my mean temperature, as I shown here, this dashed line, will be lot less, my mean temperature based definition will also fail for the mean temperature based reference temperature, as I am showing here. You can do a similar thing for LMTD, that is log mean temperature. So what really it tells is that we need a descriptor or a reference temperature that is invariant, that captures, and that is where the concept of adiabatic heat transfer coefficient and adiabatic temperature comes. As I just described to you, when there is flow over a heat source of this type, that is, there is a heat source here and a second heat source here. If both the heat sources are on, then as I told you, at this exit plane, the temperature of the air will look like this. This temperature will be close to the surface temperature of the first heat source. Then, because there is insufficient mixing, that this becomes the profile that sees the second heat source sees. It is not a uniform inlet or uniform mixed flow temperature. It will actually see a airflow temperature that looks like this. So what is the adiabatic heat transfer coefficient is, if I have a first heat source and I have a subsequent heat source, but that heat source is turned off, then this airflow temperature will rise the temperature of this heat source above its initial or local temperature, ambient temperature, above a certain value. So when this is powered off, the temperature it attains, this is the solid temperature, it is not the fluid temperature now. The temperature of the second heat source, when it is powered off, because of the influences, the first heat source, upstream heat source, is what is defined as the adiabatic heat transfer coefficient, adiabatic temperature. So we use this solid temperature, not the fluid temperature, as a way of writing our adiabatic heat transfer coefficient. So we can show, I will show in a minute, that in such a situation where there is preheating of heat source happening, a preheating of air happening to a heat source of importance. This is relevant in gas turbine industry and wherever there are preheated gas type situation arises. Even in jet impingement, when I'm looking at fluid temperature being much higher, uh, so then the adiabatic temperature is the real descriptor that one can use. So it becomes actually an invariant descriptor in these cases as well. So that, let's look at it in some detail. This is often called a thermal wake. What I'm showing is this is the top and this is the bottom view or the cross-sectional view. So I come in at some uniform velocity, and so there is one heat source on the PCB, and the heat source is within this. You can see this green line, two green lines. That is what I have modeled as PCB, and the heat source is shown here. It is here in this case, slightly shifted because I had to shrink this. So you can see that because of conduction happening in the PCB itself, as there is airflow happening from left to right, that there is spreading of the heat in the board itself, and it has a typical characteristic of a thermal wake. If you look at a flow over a cylinder type situation, there is a wake region that is formed. Very similar to that wake region, that is a fluid flow wake. Here we see a thermal wake that is happening, and often referred as a thermal wake because of the conduction that is happening in the board. If you look at the velocity profiles that are shown here, it attains quickly a fully developed flow. It doesn't take much time to attain a fully developed flow. And note that the max temperature is 56.8 degrees Celsius that I've predicted. I've used IcePAK to do this prediction. So now that was when the heat source was embedded in the power supplied is the same, which is about 0.5 watts, I think. And so when I move the heat source from the PCB as if it was I initially modeled it as if it was in the PCB. Now I make it protrude like this. Now you see that the temperature has dropped because now I used the board as an effective means of conducting the heat even better than the previous case, even though the temperature power dissipated by this heat source and the previous heat source is same. So embedding the heat source in the PCB itself is much more challenging because of its low thermal conductivity. Here what we have provided is the heat source, and it allows a certain surface area as well, and it allows conduction. So now the temperature has dropped, and there is also, you can see that there is a recirculation region because there is a stepped down input. There is a step profile here, so the airflow comes and this is an open space. So then if I do two heat sources, now I see them, there is a flow bypass, this is a cross-sectional view, there is a recirculation zone, and as you would expect, the first heat source is slightly lower in temperature compared to the second heat source because I'm preheating the air. You can see that the air, initially this blue temperature is 20 degrees. Now when it comes, the temperature profile, you can see that the flow is not well mixed. So there is a blue region and then there is a dark blue region, a lighter color blue region. So the airflow temperature range profile looks something like this. This is on the top and close to 27 degrees when it approaches the heat source. So that is the one of the important things that to remember is that now what is adiabatic temperature? Here I have both the heat sources turned on. So in order to find the adiabatic temperature of the second heat source, I have to power it off. So if I power off, I get a temperature of 24.7 degrees Celsius. If I do a mixed mean temperature, that is essentially calculate a mean temperature based on my heat input from the power that was supplied by the first heat source, then my mean temperature will be 20.5, but my adiabatic temperature is 24.7. So that means I have a 4.1 degrees C or 4.2 degrees C higher temperature as my reference temperature. So if I go calculate a temperature based on mean temperature, heat transfer coefficient based on mean temperature, the first heat transfer coefficient will be 56.5 watts per meter square Kelvin. The second source will say 44.5. However, if I use the adiabatic temperature based definition, then I see that both of them are almost close. This is due to some numerical error. I didn't do a fine mesh or anything like that. However, you can see that because of the invariant descriptor, that is a adiabatic temperature, was used as a reference temperature. Now all the heat sources will see equal heat transfer coefficient. That is what is needed to use the right for us to use the right correlation. We need to use adiabatic temperature. So people have shown this experimentally as well. For example, Professor Moffat, he had shown it back in 1998 that when I have flow over a bunch of heat sources, then this top line is the heat transfer coefficient obtained using adiabatic temperature, and these are the local power levels of the heat sources, and the bottom one is mean temperature based heat transfer coefficient, and you can see that the adiabatic temperature based heat transfer coefficient is almost constant, that is, it is invariable. However, the mean temperature based heat transfer coefficient is quite different. Only at very high power levels it starts to get closer, or it becomes flat. So again, for such complex situations where there are multiple heat sources, one has to use the so-called adiabatic heat transfer coefficient or adiabatic temperature. So is there any question? I kept going. Dr. Deshmukh, you may have used adiabatic temperature for some of your work with Professor Vedala. I don't know. Is that right? Okay. We'll just move on. Here, the interpretation of adiabatic heat transfer coefficient. A heat transfer coefficient or heat transfer rate Q is equal to the adiabatic heat transfer coefficient times the surface area times bracket is, this is the Newton's law of cooling, and T naught is the temperature of the wall minus T adiabatic. T adiabatic is obtained because of preheating of prior heat sources. Now one can rewrite this expression as wall temperature is equal to adiabatic temperature plus Q divided by the adiabatic heat transfer coefficient times surface area. Now if I subtract and add inlet temperature on both sides, essentially add, subtract on left side and move the added inlet temperature to the right hand side, then I have this grouping, Then I can again add mean temperature, add and subtract to the right hand side. Then I get this expression. That is T wall minus T inlet is equal to mean temperature minus T inlet plus adiabatic temperature minus T mean plus this. This is this. So this grouping can be looked up as how do I use this adiabatic heat transfer coefficient to improve my performance. If this difference, which is mean temperature and inlet temperature, that delta is higher, that means I have to mix the flow, because if I mix the flow very well, I will obtain the inlet temperature. So I have to increase. I made a mistake here. If the difference, that is the mean temperature minus inlet temperature, is higher, that means I have to increase the flow. That is the overall increase in temperature in the air side. If I want to reduce that mean flow outlet temperature, then I have to increase the flow. On the other hand, if my adiabatic temperature and the difference between adiabatic temperature and mean temperature is higher, then I have to mix the flow better. So I have to provide some sort of flow, put some sort of cross flow cylinders or mesh or something that allows mixing. So in some circuit pack designs, people use circular cylinders in cross flow to allow for such mixing. And the third one is the self-heating case, that is heat transfer obtained from the heat source itself. In that case, in order to increase that reduce that delta T uh, due to self-heating, then one increases turbulent intensity or does some sort of a vortex generator or some such thing. So that's how we can interpret the heat transfer coefficient. One can spend a little bit more time in developing much more detailed way of calculating this adiabatic heat transfer coefficient by using what is called superposition kernel function. And for this work is actually by Professor Moffat from Stanford, and he had done really the first principles experiments to show how one can use what we already know to develop a somewhat of a general principle for these boards. So as I discussed to you before, this is an inlet temperature. We have three heat sources, Q1, Q2 and Q3, and there is flow that is happening over it. To the temperature profile, this is the airflow mean temperature that rises and becomes flat because there is no heat source here, and then it again rises because of the second heat source, and again it rises for the third heat source, and then the mean temperature stays constant because there is no further heat source. That's the mean temperature profile. So you can use this idea roughly using the so-called fully developed flow region, because in many situations, as I showed you in the IcePAK software plot, that the flow becomes fully developed quickly and becomes quickly. And even for such cases, one can write the energy equation of this form. So this is well documented in Pace and Crawford textbook, that if I have a tube whose outer wall flux is varying arbitrarily as a function of its length, then you can see this boundary condition that is specified here, right here. At the outer wall, the boundary condition is such that the flux is a function of x, arbitrary. So like you would have in the previous case that we just, so there is zero flux, flux, zero flux, 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 zero. It can vary any way it wants. So in such situation, there is a general solution that was obtained, and using the principle of superposition, one can even add more heat sources to it, because this equation is linear, and so we can make use of superposition principle. And this is called this. This solution is there. I won't go into the details. I'm just sharing for the for completion. And so this function G is called superposition kernel function. One can use that and describe some of the adiabatic wall temperature based balances for when you have multiple heat sources and write it to generic form. I will upload that journal paper as well along with this notes. Are interested in reading it. In adiabatic temperature, I've already discussed. I'm just going to leave this as is, and then you can write the whole expression from this, and you can even do labs experiments in for UG students or PG students using this principle, and again describe like I described here what obtain the temperature differences and describe mean increase the mixing, increase the turbulent intensity, all those things in the experiments as well. So how do I measure superposition kernel function is if I have 10 heat sources, you turn only one heat source on, switch off others, obtain their temperatures. So of the other powered off heat sources, that gives adiabatic temperature. So you do the same thing and then you define heat transfer coefficient and so on. So that can be done, and even a very good correlation can be obtained for a given system with that kind of procedure. I will not do that here and stop at this point. And this is the sort of an overview. There is something called discrete Green's function developed by Professor John Eaton, and that is also quite a useful methodology to analyze these multiple heat sources. However, it involves computations to be done on top of experiments. So you have to have computations as well as experiments to be done to make use of those discrete Green's function. So I will not discuss that, just to mention it here. Then how do I enhance heat transfer? This I'm very sure you are well aware of. There are many ways to enhance heat transfer. Protrusions, vibrations, electric fields, this, that. You can stagger the chips. You can include wires, cylinders in cross flow, modulate the flow. You can even put a fan algorithm such that you can modulate the flow at an appropriate frequency, so that, and because whenever you have flow modulation, that thins the boundary layer, so that also improves. Then the second one is to include what is called winglets, delta wing vortex generators. When you put flow, you can see the flow direction is this way, and if you put these vortex generators, they induce vortices, and if the vortices are longitudinal, then you get enhancement. If the vortex or transverse, you don't get enhancement, but you only get mixing. So longitudinal vortices not only mixes the flow but also enhances heat transfer, because then there are something called scoops like this that also is shown to have better performance, enhanced heat transfer coefficients. And then there are jet impingements, foams, and so on. Some of these heat sink techniques I will discuss in either start the discussion today or I'll do it tomorrow. And as I said, the vortices can be shed whenever you have a flow over a very sharp blade or some sort of a cylinder. For example, here, these are called transverse vortices, and transverse vortices are known to only provide a certain amount of mixing. They don't do much heat transfer enhancement. However, if you shed longitudinal vortices, there is boundary layer thinning that happens, and so the longitudinal vortices are preferred, and you can obtain longitudinal vortices using these so-called delta winglets, as you can see here. These delta winglets, when there is flow happening over them, they shed these longitudinal vortices, and delta winglets have shown to improve performance by 5 to 10% heat transfer enhancement for a very small penalty of 1% penalty in pressure drop. So overall, there is a enhancement with these delta winglets. So That's a very fast, quick overview of heat transfer enhancement from these post convection. There are many methods by which people do these things. So discussing all the possible enhancement is really not feasible. I'm going to stop sharing now. So here's a software that that is often used in electronics cooling called IcePAK, and I'll just briefly introduce it. It is quite friendly for ice for people in the electronics cooling industry. Some of you may know. However, I'll just do a simple overview. Whenever you to IcePAK, this is the first screen that comes. It will ask for whether existing file or new file. So you open, always get this so-called cabinet. You can see this cabinet that is shown, and usually it has some certain dimensions. This cabinet is like a, a, a box that is used in desktop or outer box in a server board or some such thing. So so this cabinet always shows up at the beginning. Then now I want to simulate flow over a flat plate, and so I can double click this cabinet and get, I just want to say that this cabinet, I don't want 1 meter, so I'm gonna adjust it to 0.1 meter, and I'm gonna make the height to be some 2 and width 0.25. Then I say fit. Then I want to specify that there is airflow coming in from the Z minimum Z direction. So I can say that will be an opening for me. You can see that at minimum Z it has created some sort of an opening, and the second side also I'm going to create an opening. So that's it. Now I have created a cabinet where there is an inlet, and now the top and bottom are walls, side left and right are also walls. So that completes my cabinet. So if you see, there are a number of options that they have created. You can simulate, create openings, you can create periodic boundaries, you can create grills. Like I can make this a grill. Like in a desktop, you will see that the front side is there is a grill so that they can filtration. Then this I can show sources, create sources here, meaning heat transfer, heat sources. Then you can import, create a printed circuit board as well. And so there are a number of, you can put a fan. If I am a fan, I have to specify what the fan curve looks like. You can create heat sinks. So there's a number of options here. And if I want to import a geometry, that also can be done. Create an object. You can see some of these objects that are already created for the electronics cooling people. Then I can even import a CAD data. Somewhere you may have done in a SolidWorks or Pro Engineer. So those can be imported as well. And so there are macros that are already set up, like thermoelectric cooler and other the heat pipes, for example, are here. Data center components. CRAC is the computer room air conditioning. PDU is power distribution unit. Rack, tile, rack, and all. So many cases are there, and so you can. This is essentially created for electronics cooling in particular. So I'll do a very simple calculation to that this is a very easy way to use it. So I'm going to call this a PCB. I've created what is called a block. I will call it PCB, and I can change the default color to some green color or something like that, so that it looks like a um, and I have to go to the geometry, saying that my extent of this is going to be 0. And there are properties like hollow, solid, and all. I'm going to treat this board as, and I have to specify the material. And there is something called FR4. FR4 is the typical board PCB, so I'm going to apply that as the material for that. And on top of it, so for this heat source, I'm just going to specify some power that it will dissipate 1 watt. Maybe that is too much. 0.25 watts. Um, so this will be a Z velocity. So if I pressure outlet condition and velocity inlet condition, then I have that is needed to solve this. So one of the advantages is you don't have to create a grid. It usually creates by itself. But however, for better solution, one needs to create a. Here I'm just doing it for the sake of demonstration. So already it has created a mesh and it has completed the calculations as well. So now I'm ready to look at the results. I can see that there is some heat source. So there is flow vectors. So the flow is entering from the right hand side as a uniform flow, and develop flow by the time it gets to the heat source. The heat source is placed right on top of the PCB, and it sees that uh, there's some amount of spreading in the board, even though the board has very low thermal conductivity, and the temperature has rise. I mean, the initial temperature is 20, and it has gotten up to 39 degrees, even for 0.2 watts of heat dissipation, because the heat source size is fairly small. So studies very quickly especially if you're looking to model a fan, then you can specify a fan and put swirl angles. So many things can be done. So is quite in software available at the institute. Course electronic cooling course can be, if IcePAK is available, then it becomes a very useful tool for the students to learn. I know I have not touched all the aspects of it, but if there are specific questions, I can easily ask you. And there are, of course, points where we can the temperature of these probing points, monitor points, so on and so forth. So it has lots of very good features, specifically so this I have in my previous jobs, and it is quite useful to have the software for the students to use. Okay, and the adiabatic temperature that I talked about can be easily simulated here by maybe I can do that as well. So if I can replicate that heat source, anyway, I won't do it. The procedure is to um, that you put another heat source first. If this is the airflow direction, you put a heat source, then you measure the temperature of the heat source by not applying any power to it. That the temperature, you use that adiabatic temperature to calculate a heat transfer coefficient for heat source, and inlet temperature and static temperature for the first heat source is same. Stop this very brief introduction to. If you have questions, I'll be very happy to discuss tomorrow as well, or the next week as well, if you happen to explore it, come back. It does have variety of options like data center components, has a heat pipe model, thermoelectric module, heat sink models. There are lots of options there. So you can even do network modeling, like a capacitance resistance type modeling as well. Where is this? Okay, so that was a very fast, rapid introduction to IcePAK. Um, Coming back to this force convection, we already saw some aspects of it. So I'll go to heat sinks. Shall we take a break? Because instead of starting heat sinks now, I'll start after a break.
Sure, sir. Sir, also I was looking up the Moodle site. I couldn't find the recordings or the
Ah,
previous class sessions PPTs. So
yeah,
it will
I,
really help
I,
if this could
yeah,
be uploaded.
yeah. So I did announce very early today. So I spoke to the coordinators here. They said they will put it on YouTube. However, what I'll do is Moodle uh, is unable to handle the megabytes. It doesn't have sufficient storage space. So what I will do is I've already created a Google Drive uh, for this. So I will upload all the videos there and share it tonight. Because I had the discussion with them very late this week. So I will share the videos. I don't know when they will put it on YouTube. They are putting it through an official IIT Bombay QIP channel. That I don't know when they will do. However, what I'll do is I have all your emails. So individually, I'll send the Google Drive share link, and you should get it today.
Thank you, sir. Thank you. That will help.
Yeah, and the Moodle will also. I will try to put the PDFs of the material because I'm speaking from the slides. It is going little fast. Uh, but uh, but anyway, I will upload those notes. Uh, okay. We'll just take a quick break. So right now it is 3:15. I think we'll meet at 3:30.